KISSA 1D allows one to define reaction mechanisms that involve dynamic adsorption of dissolved species. Adsorbed species can then take part in reactions either with bulk or adsorbed reagents. Let us consider a sample reaction mechanism supplied together with KISSA 1D, which can be loaded from the program folder using the Load Mechanism button on the tool panel or through File Load Mechanism menu. To see or modify reactions and/or their parameters, click the Mechanism Parameters button. The reaction scheme consists of two EC processes involving solution species and their adsorbed counterparts. In KISSA notation, adsorbed species are denoted with the @ sign following a species name. For each adsorbed species, an adsorption-desorption step must be defined, as you can see in the last three steps of the mechanism. If a species cannot desorb, such a step can be made irreversible at a later stage. For solution species, one must set their bulk concentrations and diffusion coefficients, while for adsorbed ones, their initial and saturation surface concentrations must be defined. Initial concentrations can be set either as absolute concentrations or as relative surface coverages. In this case, initial concentrations are zero, but they reach their nearly equilibrium values while the electrode is held in the solution for 50 seconds at its rest potential before the voltammetric scan. This rest period, whose duration and potential are set on the potential step, is long enough for the diffusion layer developing from the electrode surface to reach the boundary of the stagnant layer of solution. Therefore, the effect of natural convection on the mass transport in this system should be taken into account, as done in this case. Delta here is the thickness of the stagnant layer. Parameters of electron transfer steps are as usual for the Butler-Volmer formulation. Adsorption steps are characterized by the adsorption and desorption rate constants, or by the adsorption rate constant and equilibrium constant beta. At equilibrium, adsorption-desorption follows the Langmuir isotherm. Note that the value of E0 for the electron transfer in the adsorbed state cannot be changed, and there is a lock next to it. This is because the thermodynamics of this reaction are dependent on other reactions and are calculated automatically. The list of reactions defining the value of E0 can be seen by clicking the Lock button. Any one of these reactions can be made dependent instead of the electron transfer step if necessary. The parameters of the chemical step in the adsorbed state appear on the next tab. This reaction is also thermodynamically dependent, and its equilibrium constant cannot be changed directly. On the potentials tab, cyclic voltammetry is chosen for the electrode polarization with a scan rate of 100 volts per second. As mentioned before, prior to the voltammetric scan, the electrode rests in the solution to allow pre-equilibration of concentration distributions of free and adsorbed species. In this case, rest potential coincides with the scan starting potential, and rest period duration is 50 seconds. Reactions are assumed to occur at a planar electrode with surface area of 1 square millimeter. Clicking Start Simulation button launches computations. When they are completed, the electrochemical current is displayed. The voltammogram displays two peaks, the first of which is due to the reaction proceeding through the adsorbed path, while the second peak is due to dissolved species. These two current components can be displayed by expanding the current values panel on the right-hand side. The values of the total current and its components, shown on the right-hand side, correspond to the time moment and the respective potential selected using the slider at the bottom of the window. Computed surface coverage by adsorbed species are accessible by clicking the Surface Concentrations button on the tool panel. Again, the values displayed on the right-hand side correspond to the time selected using the slider at the bottom of the window.